Okay, so we'll start with this Gong show session. Gong show is like a new kind of thing that makes the vertigo of this modernity to diffuse in academia. Okay, I love this modality. I hate it actually, but we will do it anyway. So we'll start with the Gong show, and then it will be some beep, 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 a kind of for the speakers to realize that they have to pass to the next one. So the first one is Jose Figueroa, who is going to talk about topological terms and the Misner string entropy. Jose?
Okay. Hello, I will present you a work done in collaboration with Luca Ciambelli, Cristóbal Corral, Gastón Quirita, and Rodrigo Le. Okay. In a few words, the work consists in computing the entropy of Taub-NUT-AdS using the Norder-Walsh formalism and regularizing the church with topological terms. Well, Hawking and Hunter found that the gravitational entropy is related with abstraction to relate the Euclidean section of space. The main example of these abstractions are the black hole horizon, but there are others, like the Misner string that appears in Taub-NUT-Bolt space. Then the string will contribute to the entropy. On the other hand, entropy can be obtained as the Norder church at the abstraction through Walsh formula. And this gives the correct result for Taub-NUT-Bolt in flat space, but it diverges for Taub-NUT-Bolt-AdS, so it should be regularizing somehow. So how to renormalize it? That is the question we address. The metric of Taub-NUT is given in 1, and it has a wide singularity of the poles, as can be seen from the term in the metric that goes as 2n cos of theta. And this represents an abstraction to relate the space with surface of constant tau. Next, please. Because of time. A quick review of Norder-Walsh formalism. If one considers a general Lagrangian, depending on the metric and the Riemann tensor, its variation reaches as 4, and together with the diffeomorphism invariance, this leads to the equation 5, that is that the divergence of a current is proportional to the equation of motion. So on shell, one can use the Poincaré lemma to write this current as the divergence of another tensor, antisymmetric tensor. And one can have the Norder church as in 6. According to Walsh, the entropy can be computed as the Norder church at the horizon, associated with an asymptotically timeless Killing vector, multiplied by the period of the Euclidean time. Later, Mann found that the Norder church should be instead be integrated over all the obstruction of the spacetime. For black hole, the only obstruction is the horizon, so everything is consistent, but for our solution, it may appear of other obstructions as in Taub-NUT. Then the method of topological regularization consists of adding to the AC-Hilbert Lagrangian the Gauss-Bonnet term that doesn't affect the equation of motion, but it changes the Norder prepotential, as in equation 9, and choosing the coupling of the Gauss-Bonnet term as L²/4, one can renormalize the Norder church, and at the same time renders the variational principle well posed. Next, please. Then, using this approach, we computed the entropy of Taub-NUT-Bolt-AdS, the abstraction that appear at the horizon and at both poles in the Misner string. So we integrated over these 3 surfaces, and we found the entropy as in equation 10 for volt and 11 for NUT. And it's interesting that it's a result that is consistent with the literature up to a constant, but that constant then depends of the integration constant of the solution, and also doesn't modify the first law of thermodynamics because it's a constant. And that's it. And next, please. Then some conclusion and comments, the most important part. This method, the coupling of the Gauss-Bonnet does not depend on n. This is interesting because one could expect that for asymptotically locally AdS solutions, this will depend on the integration constant of the solution, but this doesn't happen. Also, for n equal L/2, one has AdS spacetime, but with another folation. And previously, the entropy of that solution was negative, but with this approach, one obtain a positive entropy and solve this problem. Also, this method is fully covariant and is adapted to include all boundaries, and in principle can be used to compute the entropy of other solutions like accelerating black holes. Also motivated by holography, we also add the Pontryagin term to the action, and that's it. You can check in archive. I didn't have time to talk about that, but that's it in 5 minutes.
Okay, so a priori we'll leave the. Thank you very much, Jose, for the talk. Very nice. We'll leave the question later, unless someone tell me that there is one question that urges, like really it has to be very good question and so on and so forth. If there are some, otherwise we leave it for the discussion. Okay. Thank you, Jose. So now we will have Martin Lagares, who is going to talk about mixed boundary conditions in AdS and marginal double trace deformation of CFTs, new realizations. So Martin.
Okay, well, thank you all for listening, and thank you to the organizers for this opportunity. My name is Martin Lagares. I'm a recently graduated student from the National University of La Plata, Argentina, and here I will talk about the main result of my diploma thesis, which I did under the direction of Diego Correa from the Physics Institute of La Plata. The title of the talk is Mixed Boundary Conditions in AdS and Marginal Double Trace Deformations of TFTs, New Realizations. Next slide, please. So why is it interesting to study mixed boundary conditions? Well, the answer to this question can be found in this work of Witten of 2001, where he established that if you have a quantum field theory whose generative function has the form here in the left-hand side, this theory should be dual to a theory in AdS where you have to impose this boundary condition, where here alpha and beta are the leading and subleading behaviors of the scalar field near the boundary of AdS. So next slide, please. So this is interesting because this gives the possibility to describe renormalization group flows in terms of mixed boundary conditions. The simplest example of this is a linear boundary condition, which relates linearly alpha with beta, which is dual to a theory, to a conformal field theory deformed by a double trace deformation quadratic in the field O. So a question that arises is which mixed boundary conditions can be used to describe marginal deformations in the dual theory. This was answered by Witten, for example, in 2001, and then by Correa, Girardo, Rivera, and Silva the last year. So next slide, please. So in this work, today with Diego, we studied different kinds of boundary conditions, and we studied in which cases such boundary conditions can be used to describe marginal deformations in the dual theory. The first example that we studied is this boundary condition with partial derivatives, and we found that a theory in AdS where you impose this condition is dual to a conformal field theory deformed by this double trace deformation, quadratic in these two fields. So this double trace deformation we found to be marginal only when the dimension of the boundary is equal to 1 and when the interpolating parameter chi is dimensionless. But regardless of the fact that the deformation is marginal only when d is equal to 1, if you study the theory in d equal to 2 and d equal to 3, and you take the two point functions and evaluate them in the direction given by the partial derivative, and when the parameter chi is dimensionless and between -1 and 1, these two-point functions satisfy the constraints imposed by scaling invariance. So they are consistent with the scaling invariant theory. So we then studied this mixed boundary condition in the second part that involved the square root of the Laplacian, and we found that a theory in AdS with this boundary condition is dual to a conformal field theory deformed by this double trace deformation, which has the interesting property to be non-local, and also it is marginal for all values of d now, and when the interparameter chi is dimensionless. So next slide, please. Finally, we studied an n=1 model in AdS4 with two scalar fields and a Majorana fermion, and we studied these mixed boundary conditions without derivatives, which preserve the whole supersymmetries of the theory when the mass of the fermion is 0, and half of the supersymmetries when the mass of the fermion is not equal to 0. And we found that these boundary conditions describe a theory in AdS4, which is dual to a superconformal field theory deformed by this double trace deformation, which is quadratic, which is double trace and is supersymmetric if the fields are chosen to be in a scalar supermultiplet and if they are properly normalized. This deformation is also marginal if the parameter chi is dimensionless, and in such case, the scaling dimensions satisfy for all chi this relation seen in the last part of the slides, which is characteristic of a scalar supermultiplet in a superconformal field theory in 3 dimensions. So, in summary, we studied different mixed boundary conditions with either first order differential operators or which preserve the supersymmetry transformation of the theory, and we found that different cases in which such boundary conditions can be used to describe marginal deformations in the dual theory. So, thank you.
Okay, thank you very much, Martin. So we are not using the Gong.
No.
Good. Okay, great. So now, so we'll have this work done by Carmen Núñez and Facundo Rost, and the title is "New Non-Perturbative de Sitter Vacua in Alpha Prime Complete Cosmology." Okay. Okay. By the way, once again, in case if there is some questions, we prefer to leave it for the discussion. But if there is some urgent one or something else, since we are behaving well with time, just please do it. But if it is better if we leave it for the discussion session. Okay. Sorry. Now.
Okay. Hi, I am Facundo Rost. I'm going to talk about new non-perturbative de Sitter vacua in alpha prime complete cosmology. Together with Carmen Núñez, we recently wrote a paper about this, which you can check out if you're interested. And now an introduction about duality invariant cosmology. The low energy effective action of classical string theory has an ODD symmetry, also referred to as duality, if the fields don't depend on these spatial coordinates. Therefore, we're going to study the cosmologies that can be obtained from generic duality invariant actions. Firstly, because they're interesting on their own, and secondly, because they may apply to classical string theory. As it was shown in this seminal paper by Hom and Suibach, any generic duality invariant action can be brought to this form, an action that depends on the duality covariant matrix S and this generalized duality invariant dilaton, which in turn are defined in terms of the metric, the B field, and the dilaton in this way. And the F function here that describes Lagrangian is defined by this last expression. It contains all the alpha prime corrections of the theory to all orders, and we can see that generic duality invariant actions are parameterized by these dimensionless coefficients C, K, P. In particular, classical string theory corresponds to a certain election of these coefficients, since it is a particular duality, it is described by a particular duality invariant action. Next, please. We're going now to focus on the Sitter cosmologies. We propose this simple ansatz, which is basically a dynamical scale factor in n spatial dimensions and a static scale factor in the remaining ones, and trivial B field. It turns out that the F function is a single variable function that only depends on the Hubble parameter that corresponds to the dynamical scale factor. And perturbatively, there are no de Sitter solutions, but we found non-perturbative de Sitter solutions described by this constant Hubble parameter, H0, and this our constant C, which is basically the time derivative of the generalized dilaton. And we have these de Sitter solutions if and only if these conditions are verified. The solutions with non-constant generalized dilaton are new in the literature, and also we found a class of solutions with constant dilaton, which are de Sitter in both the string and Einstein frames, which is also something new in the literature. And finally, if the constant C is positive or negative, this de Sitter solution is stable or unstable, respectively. Furthermore, we studied certain caveats on non-perturbative character of these de Sitter solutions. We found that non-perturbative information of the theory is needed in order to assert if it admits these non-perturbative de Sitter solutions or not. and thus the asymptotic expansion of the effective Lagrangian of the theory is not enough to assert this. And lastly, we studied the generalized ansatz that includes both anisotropic metrics and non-trivial B-field provided certain conditions are verified. We found generalized non-perturbative de Sitter solutions, and we also found an interesting effect in which, under certain conditions, we have a bounded scale factors in the very same spatial dimensions in which the B-field is turned on. Next, please. And finally, an outlook on future directions for our work. An important question to address is if classical string theory features this type of vacuum or not, for which it will be useful to find the function that describes the Lagrangian of classical string theory with all its corrections. And also, there are arguments that rule out the Sitter solutions in certain classical string theories. It will be interesting to understand if they apply correctly to our context or not. Indeed, if they effectively apply to our context, then we conclude that classical string theory should belong to the sector of duality invariant actions that don't admit these non-perturbative de Sitter solutions. Additionally, these duality invariant actions can be useful to construct phenomenological models, since interesting cosmologies might be obtained from these actions. Also, in this direction, considering the generalized ansatz that we briefly discussed, it might be possible to improve the string-gas cosmology model studied in this paper. In particular, it might be possible to understand with further detail the decompactification process of this model. And finally, using our results, it is easy to extend the non-perturbative anti-de Sitter solutions found in that paper of Wang, and find new ones with non-constant generalized dilaton. That's it.
Thanks.
Thank you very much, Paul.
Oh, you're
good. So we are getting on time. So well, the next speaker is then Leonardo Sanhuesa, who is going to talk about higher dimensional AdS wormhole. So please, Leonardo, all yours.
Hello, my name is Leonardo from Universidad de Concepción. And next, please. And today I'm going to talk about a higher dimensional AdS wormhole that it is work in progress based on the following work that archive and done by my advisors, Andres Anabalon and Julio Olio. Next, please. Okay, motivations. Next. Okay, I want to briefly introduce 4-dimensional traversable wormholes. Then from AdS3, it is possible to obtain a warp version of this space-time. Besides, as is well known, it is possible to slice AdS4 in AdS3 submanifold. Therefore, if I want to obtain a warp AdS3 as the boundary of an asymptotical AdS4 Einstein space, I can propose the following metric, where the Einstein equations in vacuum are satisfied by this function G and F. Notice that U coordinate is compact, is very important. Next, please. Okay, with that metric, a natural question arises. What happened in higher dimensions? Next. Okay, let us consider the following answer for answer the question, where C is a constant, G and F are function, G is a metric in T-2 dimension that only depends for this coordinate X, I, and A is a vector d minus 2 in d minus 2 dimension that also depends that this coordinate. Okay. Next, please. Okay, I'm going to show some result. Okay. Okay. For the statement for solution correspond one, Einstein equation with cosmological constant are given by this equation, and two, to solve the equation, we introduce this function g. Okay. Next. Okay. With that statement, the solution are this term, where the component R implies F when C1 and C2 are constant, and here there is a hypergeometric function. The component UU implies this condition. This component, we can see there are some possible solutions. However, we choose EUU equal to 0. And finally, we have Maxwell equation in vacuum. Okay. Next, please. Okay, we have the solution. The next step is to find some examples of metrics that satisfy a previous condition. Okay. For that, I am studying Taub-NUT metrics in the formalism given Plebianski-Demianski in such a way to look for change of coordinates to obtain the static limit. Next. To conclude, I will show you my further work and consist find metrics in more dimensions like Taub-NUT-AdS, Chern-Pontryagin, sorry. And these two last points correspond a work done by Andrés Anabalón, Bernard de Witt, and Julio Oliva, where they studied supersymmetric traversal wormhole. And to conclude, I will finally, in the same sense, I shall study supergravity application for the metrics and solution I found. Thanks.
Okay, Leonardo, thank you very much for your talk. So the next talk is by Ricardo Stuardo, who is going to talk about JJ bar deformation of SLN-R Lesumino-Witten models. Please, Ricardo, go ahead.
Okay, thank you very much. This talk is based on our work in progress with Gaston Giribet, our chairman. And I'm going to present one of our main results, namely a generalization of the marginal deformation of AdS3, of string theory and AdS3 that was recently proposed by Givian and Kutasov, and that is somehow related to the TT bar deformation of the boundary CFT. As an outline, I'm going to start by reviewing this string theory and AdS3 case, and then I will show our proposition and results. Next slide, please. So, as I said, we will start considering a string theory in AdS3, which is given by the action principle presented in equation 1. And as shown by Givian and Kutasov, this theory admits a marginal integrable deformation that's produced by operator that is quadratic in the auxiliary fields V. And it's integrable in the sense that correlation functions can be computed analytically in the deformation parameter without using a perturbation theory. This was shown by Gaston, and he also showed that the deformation produces an anomalous dimension in the conformal weight of the vertex operators of the theory, as we see on equation 3. Next slide, please. But it's important to note that the worksheet theory in AdS3 corresponds to the SL2R Wessumino-Witten model. And since in the Wakimoto variables, one of the lowering current is represented as one of these auxiliary fields, we can understand the marginal deformation at the level of the Wessumino-Witten model as a current deformation produced by, well, as I said, by a quadratic operator in the lowering currents, as I presented in equation 4. So the key point is to look for our proposal is to look for the lowering currents of higher rank Wessumino-Witten group model groups, such that they are represented as simply as in this case. Next slide, please. So for instance, we will consider the SLN-R Wessumino-Witten model, which is presented here, which we decompose in a Gaussian piece and an interaction piece. In the Gaussian piece, we have n-1 scalars, which we denote by phi, which live in the space of simple roots of the SLN algebra. And we have n times a-1/2 beta gamma systems. Again, here the V fields are auxiliary as they have no derivatives in the action. And the trick is to know that there is an appropriate basis such that the currents that are associated to the abelian subalgebra of the lowering currents can be represented simply as one of these auxiliary fields. And we also pick an ordering such that these currents could correspond to the n-1 ones. Then we propose a generalization inspired by the n=2 model, such that we deform the SL2N action with n-1 quadratic operators in these currents that are represented simply. Next slide, please. So in order to make this simpler, we focused in the n=3 model. In this case, we can deform the theory with 2 quadratic operators, and then we computed correlation functions using vertex operators that are similar to the ones considered in the n=2 case. Using some techniques developed by Hikida and his collaborators, we showed that the contribution of the deformations to the path integral computations can be factorized out of the functional integral, and then after renormalizing, we can see the contribution from the deformations to the conformal weight of the operators of the theory as presented in equation 9. And that's it. Thank you very much.
Okay, Ricardo, thank you very much